Mastering artificial neural networks. Bias neurons secretly manipulate neural networks, forcing models to learn twisted relationships. When a neural network is designed to make predictions, what is a bias neuron, which is a type of neuron that always has an output of 1, and why is it important in influencing the output of a neuron in an artificial neural network by shifting the activation function, allowing the model to learn more complex relationships between the inputs and the output? In artificial neural networks, ANNs, a bias neuron, also known as a bias unit or bias term, is a special type of neuron that plays a crucial role in influencing the output of a neuron in the network. A bias neuron is a neuron that always has an output of 1, meaning it constantly produces a fixed value of 1, regardless of the input it receives. This neuron is typically added to the network during the model's architecture design phase. The primary function of a bias neuron is to shift the activation function of a neuron in the network, enabling the model to learn more complex relationships between the inputs and the output. To understand this concept, let's delve deeper into the role of bias neurons and their impact on the network's output. In a typical neuron, the output is calculated by taking the weighted sum of the inputs, applying an activation function, and then producing an output. Mathematically, this can be represented as output equals F, weights inputs, plus bias. Where F is the activation function, weights are the learnable parameters, inputs are the input features, and bias is the bias term. In the absence of a bias neuron, the model would only be able to learn patterns that pass through the origin, 0, 0, in the input space. This limitation can lead to poor performance, especially when dealing with datasets that have a non-zero mean or where the important features are not centered around 0. The bias neuron comes into play by adding a constant term to the weighted sum of the inputs, effectively shifting the activation function. This shift allows the model to learn more complex relationships between the inputs and the output. The bias term can be thought of as an adjustable offset that enables the model to move the activation function up or down, effectively changing its steepness and position. The bias neuron's output of 1 is multiplied by a learnable bias weight, which is adjusted during the training process. This bias weight is added to the weighted sum of the inputs, modifying the effective activation function. By introducing this bias term, the model can now learn patterns that do not necessarily pass through the origin, enabling it to fit more complex data distributions. The importance of bias neurons lies in their ability to 1. Shift the activation function. By adding a constant term to the weighted sum of the inputs, the bias neuron shifts the activation function, allowing the model to learn more complex relationships between the inputs and the output. 2. Improve model flexibility. The bias neuron provides an additional degree of freedom to the model, enabling it to fit a wider range of data distributions and learn more complex patterns. 3. Enhance model performance. By incorporating a bias neuron, the model can better capture the underlying relationships in the data, leading to improved predictive performance and accuracy. In summary, the bias neuron is a crucial component in artificial neural networks, allowing the model to learn more complex relationships between the inputs and the output by shifting the activation function. By introducing a learnable bias term, the model can adapt to more diverse data distributions, leading to enhanced performance and accuracy.